All right. Well, thank you everyone for being here. You guys hear me okay over there? All right. All right. So thank you for being here, and it's good to have you at Cognira. And I hope in this presentation I can show you a little bit more in depth what we are doing as a software as a service company that's dealing with retail. So first of all, let me introduce myself. My name is Ghaieth. You can call me G for short. I'm a software engineering manager. I've been with Cognira for 6 years and 2 months actually, and counting. The company is 8 years old, so I've been here for pretty much since the beginning, since it became a software company. And I've been involved in backend mostly, and we've been growing a good team, and we have a very big team right now, and we're working on challenging and interesting problems every day. And I'm going to share one problem that we're constantly working on with you today, and it's the calculation engine. But before I do that, let me go over a quick overview of the agenda. So first off, what is Calc Engine? Why are we going to talk about it? Some overview and background. Then talk a little bit about the design and implementation of it, how we get to actually think about it, and what we are putting in place in what we call a Calc Engine. While we are an extensive system that's heavily related on forecast and predictions, Calc Engine is not the forecasting engine that we have at Cognira. So we're gonna talk, but it integrates pretty much tightly with online forecasting. So we're gonna talk about that next. How we write the actual expressions that allow us to evaluate the metrics. I want to talk a little bit then about the history and evolution of the Calc Engine, because it's a very old project. It's existed pretty much since the beginning of the company, and it's still a work in progress. And maybe towards the end, discuss some of the recent challenges as well as the upcoming future endeavors that we want to take. So I want to start off by a slide that Greg went over, which is the overview of the architecture of Chroma AI, and let me move over this window as well. All right. Yes. So I'm just going to quickly go over this again, just to illustrate that Chroma AI is a complex system that we have. It's not a trivial one. It's probably not the most complex system out there, but it is complex enough for us. And as you can see, we have like 10 microservices. It might be too many or too little microservices. I know some companies have way more, I know some companies have less, but that's not the purpose of this talk. I just wanted to illustrate that we have a lot of ongoing things. Some of these microservices are bigger in terms of business logic that they maintain than others. But I want to zoom in a little bit now on the Calc Engine. Like I took that diagram, I zoomed in. You see the Calc Engine there. It does not interact directly with the UI, like it's not a user-facing thing, but it interacts with two of the most important microservices we have in our architecture. Those are the promotion planning and the campaign planning. And as you might have heard from Greg's talk, what Chroma AI is, we are a company that does mainly promotion planning and advertisement event planning as well. And we are not just that, but we are also a highly configurable multi-tenant software as a service company. Like that's the whole point of what we're building. We want to build something that we want to write the code once and then manage everything else through configurations whenever we can, right? So that's what Chroma AI is. It is a very important tool for our clients, for our retailers, because it helps them in their decision making on a day-to-day basis. Like they go into the system, they start playing around, they get real-time feedback on how well their promotions or how bad their promotions are going to do based on the inputs that they provide. And whether we like it or not, it's a metric-heavy system. Like wherever you go in the application, you're going to see some sort of metric that needs to be calculated or updated based on some action the user does. So that's what Chroma AI is, and that's what we are constantly working on making it like that. And just to illustrate the importance of Calc Engine in all of that, is that if we take out Calc Engine from the equation there, from the architecture, we're going to lose the ability to provide real-time custom feedback for the customers, for our customers, because there's the online version of the feedback, but also there's the offline version of the feedback, because we run nightly batches. Like overnight metrics get generated. It's not like without Calc Engine there will be no metrics. It's just that we lose the real-time online aspect of it. If we don't have a calc engine, which is this thing that we want to have configurable and abstract, that we don't have to hard code metrics and calculations in, then as Greg mentioned, like every two retailers will probably have different definitions of the same metric. Like different retailers might define a return on investment differently or slightly differently, but it's still, for our purposes, still different, and we need to code it differently. So if we don't have a generic way of doing that, it's just going to be hard-coded all over. And looking at metrics and trying to understand how something is computed basically becomes a code level investigation rather than a configuration level. And I don't know if you guys wrote or worked with data frames before, like Spark or Python or whatever. Even if the metric is simple to compute, it's not necessarily easy to understand, like to reverse engineer it and see, oh, how are we actually calculating this? Is it a sum? Is it an average? And especially if you start joining and combining data frames, it's pretty much impossible to understand what an actual formula for a given metric is. So we want to keep that benefit of this calc engine. So with that calc engine, I'm sure Chromo AI value will be greatly reduced. So having said all of those things, now we want to build it. We want to build this highly configurable microservice that's pure responsibility is basically computing stuff. And obviously we want it to be fast. We don't want something that's slow. We want it to be easy to read, easy to configure, and easy to debug. And that's the vision, that's the end game. Now, jumping into the design, before talking about calc engine per se, I don't think I can talk about it without mentioning what a promotion is, because again, we are mainly promotion planning and management company and advertising events as well. And the promotion entity and the promotion concept is very important to this company. And also Greg mentioned it in his presentation, but we defined what we call a CPL, which is the Cognira promo language, which is the unified way that everyone at this company, at Cognira, should think and thinks actually about the promotion. And this came not from day one. We kind of had to learn it the hard way, because at some of our, when working for HEB, one of our first customers, like different parts of the company had different understanding of what a promotion is, and that made the integration and the collaboration kind of hard. So after that, with the retrospective, we said, okay, what is a promotion? Let's agree on what it is, and everyone you talk to in the company should understand what you're talking about the exact same way without ambiguity. And briefly, I'm going to mention it here because later on I'm going to give examples on some aggregations and how to compute and go from one level to the next. And understanding this model is actually pretty important. And in short, I'm not going to take a long time here. A promotion is basically a set of financial conditions. The financial conditions are actually the financial contract that binds the retailer to sell you certain products within a certain dollar amount, basically. And the financial conditions have a type. Like you could go to a store and find a promotion that has $1 off or % off, or you get something for a given price, or you get something for free. And that type is important later on because many metric calculations depend on the actual type of financial condition. And obviously, a financial condition is applicable to a set of products. It's not like everything is bound by that financial condition, right? And so let's leave it at that. I mean, you can go deeper, but that's not the point of this presentation. But the common calculation patterns that we have generally is aggregations. Aggregations when you go from lower level to higher level. Spread when you go the other way around. If you type something at a high level, you want to spread it down in some way, either proportionally or like replicate the same value, or same level recalculation. So those are 95% of the cases that you need to handle. And when we first started Calc Engine, these were the expressions we had. At least we wanted them to look that way, and we actually implemented them to understand something of that sort. So for aggregation, it's going to look like, in general, like I'm going to give actual examples in the next slide, but metric at intersection. The intersection is like a collection of levels that the metric list has, like product, location, or something like that. And then equals, and then we specify an add. We don't really write add, but we replace it with a max or min or sum or whatever we want to aggregate, the aggregation we want to use. And we aggregate across another set of metrics, or maybe the same metric, but at a different level, right? And then after the where, that's where we specify the kind of the universe or the realm where the variables should live, because you kind of want to aggregate across products or stores, but which products and which stores you're going to aggregate it across, right? So I'm going to give actual examples. For the spread, same thing, it's just we use the spread operator, and for the recalc, it's pretty much simple like that, but not always, because I'm going to show you in the next slide here. Have a simple aggregation here, for example, sales at promotion, it's the sum of sales at promotion product, where the product in the products of the promotion. And for the most cases, that's the obvious part, right? You're summing across the products of the promotion. Why do we need to add it? And the reason we need to add this, be explicit here, is because we can have this situation where we need to sum across the sales of the products that only exist in the buy or in the get conditions of the promotion. And as you can see here, the where clause becomes more complex because now it's kind of compound. We say the product in promotion condition and the condition is in the get condition. And that kind of where we write it like that, and the back engine can understand it. The spread, we have two ways of spread right now: proportional, which is proportionate spreading based on some other metric or the same metric, and replication, which is you enter a value at a higher level, it just gets replicated down as it is, and we write it this way. We have this eval operator there, that's kind of does that. For the recalculations, in the previous slide I mentioned, it's simple, but sometimes when we are recalculating at the level it's different than promotion, we need the eval as well, because the eval gives us the opportunity to provide the universe where the variables live, like to provide the word clause basically. So that's replicating the revenue, that's recalculating the revenue, the margin of the promotion product level, that is calculated as the revenue at the promotion product minus the expenses. So that's kind of the syntax that we are supporting right now. And obviously, to talk about syntax and engines, we have to start talking about parse trees, and that's how we would send this expression to the calc engine so that it knows how to parse it. And it's a binary tree. We can traverse it through DFS, and from there we'll construct the bound tree, which I'll talk about in the next slide. But in terms of JSON representation, it's basically a recursive data structure. It's a JSON. Each level has the data type, the label, and the left child and right child, which can be numbered. Now, moving on to the bound tree, which is probably the most important data structure and core mechanic that exists in Calc Engine, and it's immediately induced from the parse tree. Like we traverse the parse tree, and from there we construct this bound tree. And what this is it's not a binary tree. It can, every node can have one or many children, not necessarily two. And these are actual executable nodes, and we're calling them execution nodes. And constructing this bound tree correctly is key to the smooth execution later on. Because in this case, for instance, we're fetching the minimum trade price at product store. We're doing a binary operator, and we're removing the cost. But the cost here is at the product level. You might notice these are not at the same level. So the bound tree has to be smart enough to know that it needs to add a replication here, because whatever was at the product level needs to be replicated across all stores, so that the binary operator just does the binary operation. So we want to make it such that every node doesn't have to worry about the dimensions or the levels or whatever. It just operates on its given input and just produces the output. Since I mentioned execution nodes, this is how we're defining it in Scala. It's actually pretty clean. It's a trait that every node in this tree will extend, basically. And this trait has this function that we've defined. It's called execute. We're defining it here because it's the same for every node. We don't have to redefine the execute function again and again. And what it does is it executes the children, goes to the children, executes them, and then takes the output of the children and applies the run method. The run method does nothing at this trait level, but we override it at every node. And that's what kind of makes it clean and isolated, is that if you have constructed your bound tree correctly, building the nodes and implementing them should be a no-brainer or straightforward, right? Just go to that run method. You have a node that you need to do a particular task, implement it based on the input, and return the desired output from that node, and everything else you don't have to worry about. And basically, we're creating our own defined type called result map. Result map is a map of key to value. Key is a list of string. Basically, if we have something at product store, for instance, the key will be the product ID, the location of the. That's why it's a list of string. It can be of arbitrary size depending on the intersection. The value is an execution node as well. Taking a step back, Calc Engine usually does not compute one metric at a time. It usually operates in a way that we give it a group of metrics to compute, and it computes them, right? And that group of metrics is defined or derived from the actual application workflow, because depending on the screen you are at, depending on the action that the user does, we might need to compute a different set of metrics. And so we throw a lot of equations at the Calc Engine. Calc Engine takes in, we tell it, hey, compute this group of equations. It will get all of these equations, but usually metrics depend on each other. Like if you want to compute metric A, but metric A depends on metric B, and metric B depends on metric C, then we need some sort of mechanism that tells the Calc Engine, well, you should compute metric C first, then B, then A, and that's established through this execution dependency graph, like object or class here that we're actually, it's pretty straightforward, but we're defining a couple of case classes here, field, the node, the edge, and the actual execution dependency graph. And that will be, for every given metric, Calc Engine will check this out to see what it needs to compute first before, because otherwise it will be chaos and most metrics will be incoherent and it just won't make sense. Right? In terms of memory management, I'll try to roughly describe what happens here. We have a context and a shared interfaces, and initially it was just the context. And the idea is, when we get a group of metrics to compute, they are usually for the same promotion or for a given promotion. Like Calc Engine computes one promotion at a time. It's not computing batches of promotions. And when we get that request, it's over an API call, over HTTP, we kind of need to store that information somewhere for all the other calculations to be able to happen, right? And where we store, well, the promotion type, what are the products, what's the type of the condition, is it an amount of, with the percent of, so on and so forth. We store those in the context and shared interfaces. And shared interfaces is basically, it's a collection of in-memory data structures that, if you think of SQL databases, for instance, there are tables. We write data to those tables, and then we write queries that interact with those tables to get data, insert data, and so on and so forth. That's how I like to think about those shared interfaces. Those in-memory data structures, which is there will be a lot of computations, there will be intermediate calculations, we need to store the results, we need to use the results, we need to return the results. All of that goes to those shared interfaces, and those kind of key value pairs get cleared after every computation so that we don't keep accumulating garbage. And here to illustrate the case that we can have multiple computations, this is computation 1, this is computation n. We have written data writer and data reader objects that are responsible for interactions between with the shared interfaces. And in terms of data bound tree nodes, the assign node is the only node that interacts with the data writer, and the fetch values is the only node, and the fetch set are the only nodes that interact with the data reader. Moving on to the online forecast, as I mentioned, Calc Engine is not the online forecasting capability that we have, but it integrates well with it, and we made it in a way that it should integrate seamlessly with the forecasting engine and the online forecast, because again, we need online feedback on how promotions are doing financially in terms of performance. So we did this differently for our first client, HCD, but since we had the second chance at it with Cub, we tried to do it better and lay the ground for future integrations with Calc Engine, not just with forecast node, but maybe with any other kind of third party that does some sort of calculation for which we need to use the results of and integrate them into downstream calculations. We thought, well, let's try to do it better this time. And to do it better, Calc Engine understands nodes, basically. Nodes and execution dependency graph, right? So what we said is, well, let's create a node, let's call it forecast node. It extends the execution node, it's executable, and we would need to implement the run method for that node, because that's how execution nodes work. And the run method was implemented by the online forecasting team. The Calc Engine team did not work on that code. All that we agreed on is that whatever the forecast node does needs to be written back to the shared interfaces. And that's how we would, pick up what they produced and use it in downstream calculations. And also forecast node here, it's written as an equation like other equations, so it would flow correctly through the execution dependency graph. Like if it needs to run because other metrics depend on it, then that will happen through the execution dependency graph. Now moving on to the expression helpers, a quick history here. Initially, when we first wrote Calc Engine, it was pretty simple. We were actually able to write the JSON objects manually, but then as things became more complex, we knew we needed something smarter, so we came up with the expression helpers. And after that, we knew we needed something even smarter, so we have the equation generation. And finally, we recently had the OCON configuration source of truth where we generate equations from. And this is what an expression helper looks like. Like if I had a field metric called fixed price at promotion, for instance, we define it as the sum of the fixed price and promotion condition for all the conditions in the promotion. And this syntax, this field, this add, this sum, this where, all of these are Scala helper functions that we wrote that we can combine, that at the end of the day, those produce the parse tree. And this parse tree, obviously it's a Scala object, we can serialize it, get the JSON format, and that JSON is what we actually store in the database and feed to the Calc Engine to evaluate. The benefits of this is, well, we don't have to maintain JSONs directly. We can see what's wrong with the metric more in an easier way, and it's less prone to errors. But it's not easily source controllable. We can automation out, and at the end of the day, it's still prone to errors as well, because it won't complain if you're missing a parentheses somewhere. You'll just know later on when you execute and you don't get correct results or you get something weird. So it's still prone to error. We took it one step further. We did the equation generation, which is a more structured, better way, source controllable way of writing these equations and maintaining them. And actually we realized that most metrics usually share the same aggregation or calculation pattern. So why do we need to rewrite a lot of code that looks the same if we can simplify and kind of, it's basically a code generator at the end of the day, right? And we really love this because this kind of provides everything that is needed for defining metrics at any given intersection. Like if I want to, here we're calculating, like the object name can already convey what we are actually computing, so that makes more sense when we try to find it later on. We here define the grouping because, as I mentioned, Calc Engine works on a group of equations, not just an equation at a time. We define the level where we intersect, we're calculating the metrics at. And then for every metric we say, oh, this is a sum, this is a max, this is the first state. So we're doing aggregations, right? And you might ask, what are these? Where are these coming from? Those are defined in a trait, and they have we basically want to define metrics once. Because if I go back to this original helper functions, I can define the fixed price here, but then I might need it in another equation, but I might do a typo in the other equation, and it won't work, and I will spend hours debugging it. So we needed to define the metrics once and use them wherever they needed, so that at least we don't have to worry about typos and mistakes in the names. Here's another example with recalculations. Basically, we're recalculating a metric at the promotion version product level, and it's a binary operation between two operators. That's how it would look, and actually it's pretty cool. Benefits, well, we can faster find equations that need debugging. Generating them is much easier, less error for aggregations and recalculations, and it's easily Git controllable. That actually makes sense. The limitations is, well, now I'm going to go back to talk about what we do offline, because we have online calculations and we have offline, and they need to match. But we had no centralized way of making sure that whatever we write online is going to match whatever the batch computes offline. And for that, we have to do a lot of comparisons and runs overnight and all of that. And that's because the metric definition is defined in two different places. there's no guarantee they're gonna match because there will be bugs, right? Next thing is the last thing, the whole tone parser, and this is our step, or the step we took to unify how we define metrics between online and batch at least, and so that we get the metric configuration farther apart from the code as well. Because even with the equation generation, which is the previous slide, it's still in the code. So we still need to go to source control, change the metrics, write some code, and then commit it and generate and all of that, right? We want to get it one step farther away from that. We want to have, ultimately, we want to have non-technical people be able to write equations and have the calculation be able to do that. But first of all, let's have one source of definition, one source of truth for our metrics, whether we're doing online or offline calculations. And Hocon was the way to do that. And as you can see here, we need to add more attributes now. There's this kind online because there are some metrics that are online, there are some metrics that are offline only, and there are some metrics that are both. So we need to specify what are we talking about here. We specify the intersections where we're coming from, and it's pretty similarly we define, okay, if this total saves units, it's a sum, the other thing is a max, the other thing is an approximate mean. And that kind of bridged the gap between online and offline calculations. And at the end of the day, it generates equations in JSON format. We store those, we load those into CalcEngine, and CalcEngine works. Those are the benefits that I just mentioned actually. And the brief history and evolution of the CalcEngine, well, this is a knowledge project. It started in 2018 and I was the only one working on it at the time. And it was pretty simple. Like it was doing simple promotion calculations, promotion level calculations. And the most complex situation was going from product to promotion level, like doing aggregation, right? But like it's seen a lot of movement, a lot of progress. It was not even its own microservice initially. It was part of my promotion planning service. We did not have the expression helpers; those were added later on. We made it a microservice in 2019. We didn't have the in-memory data structures keyed by computation ID, so we weren't actually able to handle concurrency. Multiple computations at the same time will collide in terms of storage, memory storage. We needed the transitive dependency. I showed you an example earlier. When we need the products and the conditions in the get conditions, like we can combine conditions so that we create a meaningful realm for the variables that we want to compute across. And then, more importantly, we added this support for match case because we realized we wanted to do it in a Scala fashion. We wanted to put together some pattern matching, but it's not really pattern matching that's advanced as Scala. It's basically we're matching on a field. Mainly, we're matching on the condition type. Is it amount of? Is it percent of? And those things. And before we did have that match case, we kind of had to rewrite the same equation differently for the different cases. But with the introduction of it, we actually can write less equations and handle more cases with just one equation. Then we added the events, we added the forecast node, we added the promotion versions and all that. This is an example of how a match case equation would look like. Here we're calculating the max VTC and depending on the condition type, if it's an amount of, we just take the amount of, if it's a percent of, we take the percent of, we can divide it by 100, and then we combine that with the price and we get the maximum value to this. This is what the boundary for a match case would look like. Here, just to illustrate that the boundary can have n children, it does not have to have 2. And here, depending on how many cases we have in a given equation, we can have multiple case nodes. Case nodes are executable. They are execution nodes, match the same thing, like it follows, everything follows the same pattern. To quickly discuss some of the recent challenges, well, we usually run into situations where we run out of memory in CalcEngine because it's a pretty memory extensive microservice, and the smallest mistake can result in a memory leak. And eventually, ultimately, that's usually always what happens. We start running out of memory, we realize, oh, we probably have a memory leak, we need to do a memory dump, investigate what's going on there. And usually we find that we have something of those shared interfaces that we're not cleaning up. And as I mentioned a couple times now, we have online versus offline. We had no easy way to validate that we're actually producing the same results besides doing runs and generating data and calculating and comparing, which could be automated a little bit better if you think about it. And just to finish, the last section is about the things that we think are missing and that we are excited to maybe find an opportunity to work on with Calc Engine. Well, as you might have noticed that I always talk about parse tree. From the starting point was the parse tree. We don't have something that takes the string representation into the parse tree automatically. All what we've been doing is finding ways to generate parse trees based on some configurations, but ultimately you should have a compiler, should have a parser, should have some validation that happens on those equations, because we can write an equation but it might make no sense and we won't know about it, right? So we need that kind of extra checks early in the process, and that will get us one step closer to having this Calc engine accessible even to the customer, not even to our product team. Like even the users could define their equations in the tools, right? Yeah, so I guess I covered that. The dependency graph that I mentioned could be smarter, we think, because again, Calc engine still relies on us, on the client, to tell it what to compute. Like, hey, compute the metrics that are needed for this screen. There are 100 metrics to compute. Calc engine will compute all of them. But that leads us to have actually many equation groups that we need to maintain, and we think we can make Calc engine smarter, a little bit smarter, so that we don't have to define that many groups, and we kind of move a little bit of the responsibility to it so that it understands what it needs to evaluate in a given computation. So intelligent dependency graph.
How's your day going?
Like,
I'm really looking forward to working on some cool stuff together.
You know, sometimes you don't need to compute everything. If something changed and only 5 metrics are impacted, no need to compute 100. Right? So we think we can make Calc engine understand that a little bit better. Distribution, right now, as I mentioned, multiple calculations happen on with the same API call. They all happen on the same replica. It's not distributed across replicas, so we think we can probably invest some time in distributed Calc engine and a bound forest, because each equation will have its own bound tree. But bound trees can share nodes, can have the exact same nodes. Can we combine all those bound trees into one forest, and then having that forest, we can probably make sure that we execute each node only once. Like if it's the same node that exists in multiple equations, no need to execute it twice. It's been there, it was created, it was evaluated. Why are you computing it again? And also, if you have a forest, we can probably detect subgraphs that are independent and do some parallel evaluations there as well. So all cool ideas that we have, and you know, as I mentioned, I think this is my last slide, but this Calc engine project is probably one of the most important microservices that we have right now in the company, because everything that you touch in the application in Promo AI invokes a calculation in some way, in some sort, right? There are user overrides, there are a lot of interactions with the system that require real-time feedback, and this Calc engine is what kind of helps facilitate that, and with minimal hard coding, if any, right? But it's also at the same time, no two people have been working on it, no more than 2 people have been working on it at any given moment, and we kind of work on it on a need basis. Like it's not like an ongoing project all the time. We realize we need to be able to handle certain situations. We go to Calc engine, we make it handle those situations. But I can only imagine what it would be if we had like top brains working on this project, and we're doing it in Scala. We could do it in another language. I mean, it's nothing that we're doing with Calc engine is Scala specific really, but it has been helpful that we did it in Scala because it's a concise and very well-defined language. It's not that verbose as Java, for example. But I also believe that there could be some Scala tools and utilities and tricks out there that we could throw at this problem that will make it even more robust and easier to maintain and easier to scale and more abstract and all that. So that's why I wanted to talk about it today. I believe there's a lot more that could be done about this project. It's a very interesting one. And thank you for your time.
Thank you.